Welcome to Organic Chemistry with Crip. This video will be an introductory video focusing on the approaches referred to in general chemistry and highlight how we will use them throughout our organic chemistry course. We begin with our theme of energy. Now, remember, energy comes in two forms: the hidden form, which we call potential, and the actual form, which you know of as kinetic. Potential energy, the hidden energy that we cannot have direct access to, measures the attractions and repulsions in a given system. And attractions make things one, repulsions make things different. Attractions always decrease potential energy, whereas repulsions always increase potential energy. Actual energy, kinetic energy, is always what is manifest. It is associated with transitions, with movement. So potential energy refers to states versus kinetic energy, a change in states. And so in reference to our simple Bohr diagram, we can see that the electron, in order to transition from a higher potential energy state, a less attracted state, to a lower potential energy state, a more attracted state, would need to release energy. And that transition would be associated with a release of energy in the form of light, and that energy would go away, so it would be associated with some kind of exothermic process, right? And then the opposite movement, to go from a lower energy state to a higher energy state, would be associated with an absorption of energy. Now, we are assuming that you are quite comfortable with the fact that electrons do not behave like particles when attracted to the nucleus, but behave effectively like three-dimensional waves, what we call a wave function. Yes, the wave function represents the radial probability of finding an electron around the nucleus, but we cannot describe the electron any other way than through its wave function. Only when an electron is emitted and it's no longer attracted to the nucleus does it behave like a particle. But when it's attracted to the nucleus, the best way that we can describe it is as a wave. So feel free to refer to the quantum mechanics videos under general chemistry to have access to the diagrams and review this principle. It's important to note that there's a key difference between the wave function and the wave function squared. What you see to the left here is the wave function squared, meaning we are not showing the phases, versus in the middle and to the right, you can clearly see phases. And that key difference is going to be important as we look and shift from atomic orbitals, which that's what these wave functions represent, and towards molecular orbitals. And this leads directly into the concept of electron configurations, specific states that electrons can take in terms of energy. So the lowest energy state for an electron is associated with 1s. Now that 1 refers to the energy level. The energy level really is telling us the total number of nodes. The total number of nodes is equal to the energy level minus 1. So 1s has no total nodes. It is the lowest energy state, and it's essentially oscillating, vibrating into and out of the nucleus surrounding it. And so that energy state, lowest energy state, right? No total nodes. Now, when we say S, what we really mean is 0 angular or planar nodes. So you can see 1s, 2s, 3s, they are always associated with 0 angular or planar nodes, versus P any p sublevel will be associated with one planar node. Now, because it's associated with one planar node, you cannot have a 1p sublevel. You can only start with 2p and 3p, 4p, and 4p, 5p, etc. Versus 3D. 3D is associated with two planar nodes. So, given that, you cannot have a 1D or 2D. You begin at 3D and so on. So, S is associated with no planar nodes, P with one planar node, D with two planar nodes, and F with three planar nodes. Of course, we can also have radial nodes, which increase the energy of the electron as we have more, if you will, spherical ripples of that electron's wave function. This is a more printer-friendly diagram of the dynamic that we have just discussed. I am assuming that you are all very comfortable with electron configurations, but perhaps even more so at this point to really be rationalizing what these wave forms mean in terms of their energies. And here we have another diagram which many of you should be familiar with, this notion that the periodic table, the organization of elements based upon their periodic properties, is directly connected to the arrangement of valence electrons, the electron configuration of those valence electrons, and so therefore associated with those reoccurring periodic properties of elements. Now, it is important to note how electrons get to higher energy states within these electron configurations. Of course, the only thing that is attracting electrons to the nucleus is the opposite charge. The electrons are negatively charged, the protons are positively charged. So, as you can see in this diagram, the greater number of protons you have, the more the energies of those electrons are shifted downward because they're more attracted, they have less potential energy, they're more attracted to the nucleus. And here you have a more dynamic diagram that I've made to illustrate this, because if we just simply compare 1s in hydrogen compared to 1s in helium compared to 1s in lithium, the attraction due to greater number of protons, right, becomes stronger and stronger and stronger. But of course, that means then we can attract more electrons. And as we have more electrons, the lower energy electrons literally repel the other electrons into higher energy states. So as we fill the lower energy states, more electrons that come in and are attracted to that nucleus, they have no other place to go but to be repelled into that higher energy state. So we can see that dynamic as we go across the periodic table, and this is directly associated with periodic trends that you learned. All of the periodic trends are really associated with. The only trend that would decrease the potential energy of the electron, right, is that greater attraction to the nucleus due to greater nuclear charge, i.e. more protons. And the other dynamics in which you have a new energy level or a new sublevel, i.e. More planar or angular nodes, right? P, D, F, or electron-electron pairing, or even shielding as we go down a group. These really are referring to this repulsions between like charges, between the negative charges, because the only way to get into a higher energy level is to be literally repelled from lower energy electrons to that higher energy state. The only way to exist in a new sublevel is to be repelled into that higher energy sublevel state. The only reason why electron-electron pairing is associated with a higher energy state is because of that repulsions in that given orbital. And of course, as we have lower energy levels filled, those exist as a shield to the attraction of higher energy electrons to the nucleus. And so therefore, those higher energy electrons are even less attracted as we fill lower energy levels. Now, all of this has referred to atomic orbitals, but now we make the shift to discussing molecular orbitals, which again, you have referred to in some way in general chemistry. That is, when you spoke of sigma or pi bonding, sigma is the Greek letter S. So just like how we had atomic orbitals that had S, P, D, F, right, associated with the sublevels, in which S is associated with no planar nodes, P with one planar node, D with two planar nodes, F with three planar nodes. Here we have with molecular orbitals, we use a different designation. We're using Greek symbols, so sigma, pi. We could refer to phi and delta, but we really won't in organic chemistry, just sigma and pi bonding. And so when we think of molecular orbitals, we have to think of them as a possible linear combination of these atomic orbitals. And that means then they could either constructively interfere with each other, that is, be in phase, or destructively interfere with each other, and be out of phase. You can see on the energy diagram that to be in phase would be associated with a greater attraction. To be out of phase would be less attractive because it would really result in this exposure of the positive charge in reference to positive charge of the nucleus and create greater repulsion in that dynamic. So the lower energy state, the more stable energy state, is that sigma bonding orbital, in which those atomic orbitals of the electron are in phase, constructively working in phase, and form this more stable state as they are more attracted to two nuclei. So the whole point of bonding, molecular bonding, bond just means an attraction. That's all bond means. So when we refer to atomic orbitals, these orbitals are bonded to just one nucleus. But when we refer to molecular orbitals, then they are attracted to two or more nuclei. And so here we have sigma bonding or pi bonding represented at the bottom here. And notice how that sigma and bonding will always result in no planar nodes. Okay, but pi bonding will result in one planar node. Just like our atomic orbital designation S meant zero planar node and P meant one planar node, sigma bonding molecular orbitals result in no planar nodes, while P molecular orbitals, pi molecular orbitals will result in one planar node. However, when we talk about antibonding molecular orbitals, really these refer to that higher energy state that will be necessary to break a chemical bond. And so we call these sigma star or pi star anti-bonding molecular orbitals. And you can see that if we place the atomic orbitals such that they are out of phase with each other, then they will generate another node, another planar node between them, which of course is associated with a higher energy state and greater repulsions. So in conclusion to this video on making the transition from atomic orbitals to molecular orbitals, we consider the fact that in molecular orbitals, we have a combination of wave functions of the atomic orbitals coming together. And so you can see for our sigma bonding molecular orbital in formaldehyde here, if we see the wave function still represents the phases, but here for carbon and oxygen in their sigma bonding, right, both of them sp2 hybridized, there is an overlap in the center, and you will see that there is a shift in that sigma bond, which matches the polarity of the bond, oxygen being more electronegative. Therefore, there's a greater electron density on the oxygen atom. But you also notice you have the other phases being represented as green on the opposite ends, right? And notice how the wave function squared provides the generalized probability of finding these electrons in that molecular orbital. Also consider how pi bonding differs from this, right? Sigma bonding will be associated with 0 planar nodes, while pi bonding will be associated with 1 planar node. Of course, in order for that pi bond to exist, those phases must be in phase, constructively interfering with each other. And so you can see that pi bond in formaldehyde. Here you have carbon and oxygen overlapping in that wave function. You can see again there is a shift towards oxygen. That's why with more electronegative atoms, when you've bonded them together, that will stabilize those electron energies as they're attracted to that more electronegative atom. Again, notice the wave function squared represents that generalized probability of finding an electron. And then finally, notice how interesting the anti-bonding dynamic occurs. Again, this is a higher energy state. Notice how in a pi star or sigma star, doesn't matter, anti-bonding molecular orbital, when you look at those atomic orbitals that are out of phase with each other, notice how carbon's atomic orbital is much larger because it is the less electronegative atom, and oxygen the more electronegative atom. For that anti-bonding molecular orbital to occur, this would have to be in a substantially higher energy state. And so we have this dynamic where it's the opposite of what we would consider the more stable state, right, in terms of polarity. And again, you can see the wave function squared as, again, representing that generalized probability of finding that electron. Well, till next time, Crip.